Hello everyone, thank you for coming to Senior Projects presentations. We are the Power Electric Group. I am Adam Larwood, Mechanical Engineer.
I'm Hunter Wilson, Mechanical Engineer.
I'm Mason Vaughn, Mechanical Engineer.
And I'm Travis Bennett, I'm also a Mechanical Engineer.
So some introductory concepts for our project. We had four key tenets we wanted to follow. First being energy from effort. The goal of our project was to take the energy used by gym goers and convert it into an electrical current. Our second tenet was stay green while getting lean. That is meant to comment on the environmental impact our project has, hoping to reduce the amount of carbon emissions used by outsourcing your power to any other companies for the gym owner. Our third tenet is spin to win. That is a commentary on the function form of our project, taking rotational energy from the cable pulley system of a cable machine and turning it into electrical energy. Finally, plug and play. We wanted our system to be as modular and unintrusive as possible, making sure they can integrate into as many cable machines across the nation.
So these are the requirements for our project. The first being we want our unit to be able to power various watt-hour light bulbs. This is going to be a tangible way that shows that our unit is capable of powering different loads. It also needs to be a small modular unit that can fit across different brands of tower machines. As many of you know, you walk into different gyms, all their cable machines are different, and we want to fit on as many as possible. It also must not impede on the functionality of the tower machine itself. Our unit needs to be small enough and out of the way of the user, just working in the background. We're also going to translate the motion via a double pulley system. And we need our unit to feature one secure way to either fix it down to the ground or weigh it down so we can maintain tension within our system to reduce the slip. And we're going to output 12 volts of DC. These are the specifications for our project. First, we've selected a 1N4005 diode for our diode rectifier bridge. This is going to allow us to generate power bidirectionally. So while the user is either lifting the weight or releasing the weight back down, we'll be harvesting the energy. This unit's also going to have infinite rotational freedom. So this is going to allow the user to use the full cable length of the tower machine for any exercise. We've also selected a DC brush motor to act as the generator in our system. We went with the brush motor because our system doesn't generate enough RPM to warrant a brushless motor, and this motor is going to have a higher efficiency for our application. We've also chosen an adjustable 12-volt 3-amp charge controller for our circuit. This can go all the way up to 24 volts and 8 amps. However, we don't see that necessary for our project, but it's there if we need it. And then we have that self-designed double pulley system that I was talking about, which is going to feature one double pulley, which is a replacement pulley that's put on the tower machine itself, and then a second double pulley that will be housed within our system, which will allow us to translate the rotational motion from the tower machine into our unit. And we've also selected a 30 millifarad supercapacitor for our circuit. This is our budget so far for our project. On the left-hand side, you can see all the items that we use either in our unit or use for testing, along with where we're sourcing them and the size if necessary. On the right-hand side is going to be the cost to us and also the real-world cost. We were allotted a $500 budget for this project, and as you can see, we're far below that, thanks to Dr. Zhu and Dr. Garishi having a lot of the things that we need for our system. Us being this far under budget is going to allow for considerations like getting a custom double pulley made for a replacement pulley for the tower machine, and to also make a full-scale model of the tower machine, as tower machines are very expensive and outside of our budget.
And just to get into the path of progress for our initial prototype at the end of the semester, there were several considerations we had to make, with our initial stages leading us actually to consider compound lifts being harnessed, which, as a bit of background, compound lifts are any lifts that requires the use of a barbell and is meant to target multiple muscle groups at the same time. As mechanically fun and complex as it was to design as mechanical engineers, we decided to stick to the KISS principle, and as you can see in our planning and workshopping phase, we stuck to cable machines as the existing belt and pulley systems within those lift machines are far better for harnessing energy in terms of a DC motor generator. As we go into the design stage, after initially calculating feasibility for the project, we wanted to go through an iterative design process to make sure we could streamline the system as much as possible and make sure it was not intrusive on existing equipment. And then finally, our prototype stage, we did end up with a prototype this semester where we hoped to simulate a full-scale model as close as possible.
So this is the schedule that we followed this far into the semester. On the left-hand side, it's all the tasks that we've done and accomplished over the semester, from in-class assignments to group work done in the background to make sure our unit was functional. In the middle is the progress column. As you can see, the majority of everything's done outside of the drawing package, and then our final design. This will be completed before the start of next semester.
So now we move on to the more physical portion of our design. The above image features one of the double pulleys that we would be using. It's really just a conjoint pulley that we would be installing at one of the load-bearing positions on a cable machine that you can see in a gym, which would run down with a band to the other double pulley that will be mounted on that stand that is at the base of our housing, which will be featured in the next slide. That pulley will be driving a DC motor, which will be clamped into a casing that is attached to the base of the housing, which then drives the rest of our circuit. If we move on to the next slide, you can also see the housing cover, which has a slit for a band to run into the double pulley house. We wanted to make sure that we have enough clearance in case the band wiggles at all, but that'll be something that we fine-tune more clearly once we actually get into the more realistic size testing phase.
So you're going to see a video in just a second here of our preliminary prototype running, hopefully. We have a video of our preliminary prototype running. I can give you a brief explanation of how we achieved that system. We essentially, on a small scale, created our own cable lift machine, which with a load-bearing pulley, the pulley that connects to your motion, and then two pulleys for keeping tension in the system. We were able to, through both the concentric and eccentric motions of the exercise, light a single LED and then conducted increased load testing with 3 LED, 2 LED, and 1 LED systems. With the 3 LED system flashing and dying out the quickest, 2 LEDs holding their charge for longer, and then 1 LED holding their charge throughout the entirety of the test. You gonna try it here? That's it.
Try hitting enable and at the top.
Oh, that would be it.
Do you have the video somewhere? Just play the video. Do you have the video somewhere? Yeah,
Because it's a drawing.
If we open it up,
We'll try to find it afterwards.
Yeah, we can get it to you guys after the presentation.
So potential energy calculations, we wanted to do this to make sure, to bring emphasis to the energy that's actually being output by the user when they're exercising using the cable equipment. We assumed a weight of 100 pounds being lifted and about a range of motion of 30 inches. And using the gravitational constant, that gets you a 340 joule output required by the user for a single repetition of the exercise. And then assuming the 3 sets of 10 reps being done, you're using about 10 kilojoules of energy in order to complete your exercise on the machine. Now that's just a single exercise being done by one person. These gyms are going to have much more traffic, so even with a low estimation of 20 exercises being completed in a day, that is 200 kilojoules of energy required by the user to complete their exercise that currently is going nowhere. So the idea is for a project to harness as much of that energy as possible. The capacity calculation helped with our circuit design. We used a 100 ohm resistor and a multimeter to measure the voltage across it when we were running our prototype. We got a max voltage of about 2.98 volts, and then assuming your time of repetition is 3 seconds, we then calculated the amps, the power, and then got a capacitance that's shown earlier of 30 millifarades.
So this is our electrical block diagram, but it's really more of a system of operations. Basically, whenever you're pulling or returning the cable to its initial position, you will be spinning the pulleys, which then drive the mounted pulley in our housing system that move the motor. That motor will be providing a current through our system that runs through a diode rectifier bridge, which then directs it to a capacitor and a charge controller in parallel, and the charge controller will be charging a battery. Now, when you're not actually moving the pulley at any point through your exercise, or if it's just a dead point while you're in the conversion phase, that capacitor will be used to discharge energy and really steady out any excess input or impulse voltage throughout movement. And then this is the circuit diagram that we have right now. Again, motor spins, goes to the diode rectifier bridge, into the capacitor charge controller, and then returns to the negative point.
This is our work breakdown structure. Our research started with seeing what was currently on the market related to energy generating exercise equipment. And what we found was that really the only thing on the market has to do with cardio equipment with exercising. So we went ahead, we were to try and start on the weightlifting application. Ran some sample calculations to test feasibility, and then the parts and cost analysis go hand in hand with figuring out design and then finding parts for it and hoping it fits our budget. The mechanical system, as previously explained, is basically just a system of pulley ratios and cables and belts. And those end up connecting from the machine that we're hooking up to down to our housing unit where the motor then spins and during the motion of the exercise. The electrical, as previously explained, basically just 4 main components. And then for the testing, we have done these small model tests, which we'll hopefully show in the video. And then the big ones to hit for our final one are the integrability. As Mason mentioned previously, there's many different designs of this cable equipment in these gyms. So it's important that we're able to fit into as many of those as possible. And in the power output capability, we want to test to see actually how much we're able to retain from the exercise movement. And then system robustness is important, as we don't want to affect the system negatively, and we want to make sure our system is sturdy and has as minimal slip as possible to be as efficient as possible. The ethics and safety, there's 2 main things that stand out. Looking at ASME Section 2, we have the engineer shall hold paramount the safety and health and welfare of the public. This is important because there's lots of weight moving around on these machines, so we want to make sure that we're not negatively affecting these machines to either impair the equipment or the user. And then on a more positive note, looking at Section 8, we have engineers shall consider the environmental impact of sustainable development with their duties. And this goes directly hand in hand with ours, as we actually aim to reduce any negative footprint that might be generated because we're looking to get energy out of something that is right now just going to waste.
We do have a picture there of what the video will show later. We can get that for you. That is the pulley system. So for our prototype and future testing plans, we started with an estimately 1/8 scale prototype to empirically verify some of our theoretical calculations. This had a focus on our proof of concept and gaining some data for larger scale calculation. Next, we want to move to printing and mounting our custom double pulley system onto about a half-scale prototype, where we can test the system robustness, stability, and structure. And then in our final full-scale prototype, we hope on making the tweaks necessary to the mechanical structure so that our system is as stable as possible and increasing efficiency, with the main focus being on obtaining our full-scale data and figures. We would like to take a moment to thank Dr. Parisi for being our advisor for this project, Dr. Zhu for providing a lot of the electrical insight and components for our prototype, and Dr. Beddoes, of course, for helping put all this together. Thank you.
Okay, so
We're looking forward.
yeah, while they're getting their video loaded, just a reminder to all the teams to embed the video that helps with the PowerPoint. And any of the teams that are coming up after lunch, if you want to make sure that your PowerPoint is working, it will be up on the computer, so don't take a look at that. I suppose we could start questions while Mason's getting that going, so if anyone has any questions. Kind of look at it.
Thank you. So, first is that your charging circuit, that resistor is extremely important in my experience. Play with that because that's basically just that resistor is basically like it's controlling the charging dynamics. So play with that. It's very sensitive. Just like it's only like 200, 300 ohms, but play with the different lines and can make a huge difference. So that was my experience.
Thank you. Okay, appreciate it.
Secondly, is keep this in mind. That's just we're engineers. If you look at it from a pure energetical perspective, anytime when you take energy out of the system, that energy has to be coming from somewhere. Right? That means what? That means if you are actually generating lots of energy, that means the user will actually feel the resistance.
Yes.
Because that's the user is putting energy into your system. So when he is actually lifting, he should feel it. Does that make sense? I mean, you may not be generating that kind of energy. Of course, I mean, that would be huge. But at least, again, from an energy kind of perspective, that energy has to be coming from somewhere, which is coming from the user. So if that guy is like, I put 20 pounds, mentally I feel 30 pounds, I mean, you see what I mean? I guess they should be aware of that, right?
Just to actually make a comment on that, due to the nature of the pulley system that most cable machines harness and how we're generating our power, it is mostly based on speed of the rep, and the resistance that you experience with relation to the motor is not as much compared to your average weight that is actually being lifted by the user. So doing our testing, we experienced a good bit of slight resistance due to the motor, but compared to 100 or 120 pounds that the user is going to be lifting, it is pretty negligible.
Absolutely, that's a very good point. See, yes, I mean, like I said, if the user is feeling, I mean, for EV, that's definitely make a difference, because if the EV is doing dynamic braking, I mean, it's definitely you are drawing power out of the system, so that's a different story. But for yours, yes, it's definitely, I wouldn't expect the user to feel anything. Otherwise, you are doing a too good of a job.
It is a consideration.
Because again, but it's a good idea for us to think about, because when you are drawing power from the system, that power has to be coming from somewhere, which is the user is putting that in your system.
Thank you for making that.
Yeah, I didn't see a diagram of your system with the weight machine to illustrate exactly what's going there. I did see that picture there
Yes.
that at least finally at the end of your presentation gave us a hint as to what's going on here.
Yeah.
So from my perspective, looking at this, it looks like your motor is just a parasitic load on what you're actually doing. Therefore, you're expecting that most of the energy the user is putting into this is not going into your motor and into your energy generation. That's just a little bit of a parasitic mode that the user isn't even supposed to notice. That really what the user's doing is he's lifting weights. So here's the issue. If you really want to generate lots of power while you're exercising the user, have the user just drive the motor through some mechanism and have the motor present a load because it's driving an electrical system that's absorbing that energy. You did something, I guess all of you guys have had mechatronics, and you had a motor driving another motor that was being used, and as you increased the load of that second motor, it was harder and harder to turn the shaft. Something like that, if you're really interested in generating energy, you just rig your pulleys to push a motor rather than bother with weights at all, and it might actually be a lot cheaper system. As it is, you're just harvesting a little bit of the energy that the users use, dissipating to run the weights up and down. Another thing you could consider doing is let the user lift the weights, and then as the weights come back down, let that drive a motor that is harvesting that potential energy and turning it into electrical potential energy. Just a few suggestions. Thank you.
Thank you.
Do you want to play your video?
So you're going to see in the middle right of the screen, the LED is lighting up on both eccentric and concentric motion. As I talked about before, it's kind of hard to see with the lights in the room, but you'll get a much closer view when we go to our different load types. Those two pulleys in the center of our system are mostly for keeping tension. Most cable machines have that feature. And this is our distributed load, and those three different variations of LEDs. Obviously, the 3 LED system, it does go, and it does stay a bit slightly on the concentric, which is the falling motion. The 2 LEDs stays on for longer, and then finally, the first LED is right throughout the entire duration with larger flashes in between. And so if anyone wanted to make a comment or question on that, that is it's also fine.
I'm just happy to see some experimental results.
Yes, we were very happy with that.
I would be really sad if I don't say this. But good job.
Thank you.
Okay. Any other questions? Everybody wants to get to lunch.
Oh, see, done.
You could test, did you measure how much power they're getting? Voltmeter?
Yes, yeah, we did that initially when figuring out what kind of capacitance for capacitors we would need in the system. We just actually took that exact motion and rather just ran through a resistor and measured on both sides to see what voltage was running through that to get an idea how to kind of, because the capacitor was needed to help kind of trickle energy more consistently throughout the system because it is an impulsive motion for the majority of the motion.
Our average voltage is around 3 volts per ground.
So normally when you're lifting, you weight go down, you don't weight down.
No, you ease it on, which is why it's how the graph would look if we were to graph it with like an actual weight monitor would be a large spike on doing the rev and then a smaller hill on releasing the rev. But yeah, we do see your point, maybe creating like a more consistent voltage. Thank you.
Thank you, team.